For some of you. Welcome to the Photonics Innovation Centre seminar series. So today we're especially delighted to have Professor Jianping Yao here to give a talk. Professor Jianping Yao is a distinguished university professor and university research chair in the School of Electrical Engineering and Computer Science at the University of Ottawa. He's got a great many titles. He's the editor-in-chief of IEEE Photonics Technology Letters, which should be very familiar to all of us. He's on the advisory editorial board of Optics Communications, again, one of the highly reputed journals. And he's on the steering committee of the IEEE OSA JLT journal. So Professor Yao is currently an elected member of the Board of Governors of IEEE Photonics Society. He's also a IEEE Distinguished Microwave Lecturer 2013 to 2015. He received a great many rewards, including the 2017 to 2018 Award for Excellence in Research of University of Ottawa, and was a recipient of the 2018 R.A. Fessenden Award for IEEE Canada. He's a fellow of IEEE, a fellow of OSA, a fellow of the Canadian Academy of Engineering, CAE, and the Royal Society of Canada. So that's a lot of awards and honor to his name. Now, it is not the first time Professor Yao gave a talk here. In fact, he gave an invited talk a few years back, right? Five years, something like that. And it was so enlightening that we decided to invite him back last year for this seminar series. But at the time COVID-19 hit and his talk was canceled. But we didn't give up, right? We chased after him, and so here he is. He's renowned for his research in microwave photonics, which is the topic of his talk today. Microwave photonics is a field that deals with the use of photonic technologies to generate, to process, control, transmit microwave signals to take advantage of the high frequency, bandwidth, and very low loss of optical fibers and photonic devices. So we're going to hear more about that and its applications in wireless communication, radar sensing, a host of applications that are in the cutting edge of technology. So please join me in welcoming Professor Jianping Yao.
Okay, thank you very much, Professor Chen, for the kind invitation. It is true that I was last time, I think, in U of T 5 years ago. And at that time, I think that you have a PhD student to defend his thesis. So I was on the committee. And after defense, I gave a talk about microwave photonics. So in 5 years, a lot of progress in this area, especially integrated microwave photonics. So people try to use, especially silicon photonics, to make you see that the system smaller and have better performance. So today, you see, the title of the talk is microphotonics, but I try to give some, you see, the new results, especially in integrated microwave photonics. So here is the outline. So first, I would like to cover a little bit about the microwave photonics. So what is microwave photonics? Because I know that, so the audience, I think many students, you see them, and perhaps 5 years ago, you were not at the U of T. So here today, I try to spend a few minutes to give introduction to microwave photonics. And then I will cover a few very important topics under this microphotonics area. The first one is the microwave generation. So how to use photonics to generate a micro signal, and why we need to do that. And then the second one is a micro signal processing. So how to process a signal using photonics. And also the third topic is true time delay beamforming. So true time delay. So we know that using photonics we can get time delay, and time delay can be used for beamforming. Beamforming is especially useful for phase array antenna. Then the last topic I will cover is a general purpose signal processor. It's using photonics. We can do this. That means that the processor can be reconfigurable or programmable. So then we can change, you see that the different parameters, and then you get different signal processing functions. Then I will conclude my talk. So what is microwave photonics? So from the title, you can see that microwave photonics is in fact is a combination of the two fields. In fact, microphotonics more precisely is that it uses light as a carrier, optical carrier, and it uses photonic and optoelectronic devices for the generation, transmission, control, and processing of microwave signals, and to upgrade microwave devices and systems. So when we need, for example, very high frequency, which cannot be implemented or difficult to implement using pure electronics, or very broad bandwidth, which is hard to implement it using pure electronics, we may do it using photonics. So usually our microphotonic system consists of a laser source, you see. And then we have a modulator. So a modulator is to translate, you see, convert a micro signal to an optical signal. So that we do the modulation. So then the signal is carried by an optical carrier. Then we do the processing. Everything is processed in the optical domain. So we, for example, get time delays, we get phase change. So all the different functions that we can implement in the optical domain. So here is the processing unit. Then after you finish process the signal, you can convert signal back to the microwave domain using a photodetector. Then that you get a microwave out. So if you put everything in a box, then you have micro in, micro out. So you may not know that the signal is processed in the optical domain, but you see that in fact it is, because we use a modulator to change the micro signal to the optical domain, and then that we do the signal processing, because you see sometimes that electronics cannot do the work, we do it using photonics, because photonics, the bandwidth is much wider. And also, for example, for microwave signal transmission, to send a micro signal over a long distance, we can do it over fiber. So fiber loss is much smaller, and also the fiber, the bandwidth is much, much greater. So here you can see that here I have a comparison between photonics and the microwave. So the motivation of using photonics is to solve, you see here we said the bottleneck problem. So the bandwidth is limited. And to make a micro devices and system to be lighter, smaller, higher frequency, and wider bandwidth. So if we compare using photonics and the microwave, you can see that the bandwidth is much, much wider than microwave. And lighter means the fiber compared to copper cable, you can see that fiber is 1.7 kilogram per kilometer compared to 567 kilogram per kilometer. It's much, much lighter. And loss, everyone know that the fiber loss is only 0.2 dB per kilometer compared to copper cable is 360 dB per kilometer. And also we know that photonics, you see, is immune to electromagnetic interference, which is also very important, especially for communications, for wireless communications applications, for radar applications. And also photonics, because we have a PIC, photonic integrated circuits, so we can make device smaller and system smaller. And also photonics we can use to perform this parallel processing. That means, for example, one example is that we use the WDM, so we carry signals over many different wavelengths. We process signal, you see that in parallel. So that is the advantage of using photonics to do micro signal generation and micro signal processing. The first topic is called the micro generation. So the principle is quite simple. If we have two wavelengths, F1, F2, so two frequencies from two laser source, then we apply the signal to a photodetector. Then we know that the photocurrent is proportional to the power, you see the input power P. And then that at the output of the photodetector, we have different terms, but the one very important term is F1 minus F2. So that is the bit frequency. So for example, if we have the laser sources working at 1550 nanometer, this wavelength is optical communication wavelength. And if the wavelength spacing between the two wavelengths is 0.8 nanometer, then at the microwave we generate the frequency is 100 gigahertz. It's very high frequency. It's difficult to generate electronically, but it's simple. You see that we use two lasers with bit, we can get high frequency microwave. And the problem is that if you look at this expression, you have phi 1 minus phi 2. That is the two-phase terms coming from two laser sources. And these two, you see that laser sources may not be phase locked. So then the quality, you see the phase noise may translate directly to the microwave domain. So then that to generate a microwave signal with low phase noise, we try to lock the two laser sources using different techniques. Okay, so here today I just give a few examples of how to generate you see a microwave using photonics. The first example is that this is in fact we did 15 years ago. It's a laser, but this laser is a fiber ring laser. We have you see that a special FBG is here, fiber gating phase shifted FBG, and we try to introduce two phase shift to introduce, you see that it's a very narrow band pass band here. You see two pass band, and we use another FBG to select these two pass band. So the combination of these two FBG, FBG1, FBG2, then you get the frequency response given here. You see that we have two very narrow pass band. And if we include this, you see that filter into this ring cavity, then we can generate two frequencies. Because the bandwidth is very narrow, so for each wavelength, it's a single frequency. So then we have two frequencies with bit, we can generate a microwave. So that is one way to generate you see a microwave using photonics. But this is fiber-based. Fiber-based, you know that if we did experiment, we know that it's very sensitive to the environmental change. So that means that you have to have a very good package, otherwise that the stability is poor. So one solution is that try to use the solid state optics. For example, here, this is another approach where we use, you see that this laser cavity, and within the cavity, we have this birefringent is the crystal here. So that means that within this cavity, along the vertical and the horizontal axis, you have, you see the two wavelengths which are different, the reason because of the birefringence. So that means that for this laser, once we have the gain, here is an active medium, so we increase the gain, then it will start to laze. Then we generate two wavelengths, and the two wavelengths, of course, is determined by the birefringence of this crystal here. And then we get, then we apply this to bit. We project these two, you see, orthogonally polarized light to one direction and apply the photodetector, we get a microwave. And also, you see, this is a crystal. If you apply the electrical field, then the birefringence can be tuned. So that means that we can get a microwave with a tunable frequency. For this particular example, so the tunable range, frequency tunable range can be from 2 to 130 gigahertz. This is huge. It's very difficult to use in electronics, but here with photonics, we can get a very large tunability. If you look at the phase noise usually you see that we try to measure. Use a signal analyzer, or you can use a high quality spectral analyzer. You can see that the phase noise, if usually we look at 10 kilohertz offset at this point. So see what is the what is the phase noise level. For example, for this particular example here, it's around, it's less than 120 dBc per hertz. So it's the phase noise is quite low. So that is a very simple, you see, architecture, but the quality of single generator is good, and the frequency tunability is very good. But this is about solid state optics. But if you look at the package device, it's still very large, very large. So the way we try to make it smaller, of course, we have to go through this PIC, the Photonic integrated circuit. So this is the work we did a few years ago using, you see that using, it's all called Reconfigurable Photonic integrated signal processor. So that is indium phosphide based. So this processor, so I'll give details about this processor next slides, but processor itself can be reconfigured to operate as you see a single processor, for example, to do this integration, differentiation, for transformation, Hilbert transformation, but also it can be reconfigured to do the microwave generation. So here I try to focus on the last point. So microwave generation, how this processor is used to generate the microwave. So this is you see that the architecture of this processor. It's an indium phosphide based, and it consists of 9 SOAs and 4 tunable couplers. So tunable couplers, you see here, 1, 2, 3, 4. And also, and we have phase modulators within this, each ring we have phase modulators. To generate microwave, what we do is that we try to, you see that for this, the first ring, we have 2 SOAs, SOA 4, SOA 5. We try to have, you see the injection current to raise the gain. So once the gain is high enough, then this resonator become a laser. It's a ring laser because you see the gain is higher than the loss. Then we start to laser. So this is the first laser. And then that we have a second ring cavity. And also we try to increase the injection current to have higher gain. Then we get the second laser. And then that we can have 2 lasers. And this the ring in the middle, these 2 SOAs are reverse biased. So that's a no light, so it's generated by this cavity, So we have only 2 cavities forming 2 ring lasers. And here we have a phase modulator. You see a phase modulator. And we can apply, you see, injection current to do the phase modulation. You change the phase means that the cavity length is changing. So that means that the wavelength can be tuned. So here, for example, here we fix the wavelength for the R1, but R3 we can change the injection current to change the wavelength. That means that we beat the 2 wavelengths, we get a tunable, you see, frequency. But here, for the experiment we did, we tried to apply this parabolic signal to this phase modulator. We know that if the phase, look at this expression here, the phase is proportional to t squared, t is time, of course. And then we know that the frequency change is d phi dt. So the frequency is linearly proportional to time t. So that means that for this laser, if we apply this waveform to this phase modulator, then this laser will generate a linear frequency changing or modulated optical wave, or we say chirped optical wave. So one laser fixed frequency, and second one is chirped. Then we beat these 2 wavelengths, we get a chirped microwave. So you can see that if you look at this waveform here, so this one, it's in fact, it is chirped. If you look at, you see that at the beginning, so that is the frequency is lower, and the very end, the frequency is higher frequency. This is chirped. So this is a chirped microwave. So chirped microwave is very important because is that we can use it for pulse compression. That is widely used, for example, for imaging, for radar, for example. So that is the way we can use this PIC to generate a chirped microwave. And the time bandwidth product, that's very important parameter to characterize, you see the chirped waveform is very, very large. So that means that the path compression ratio is almost identical to the time bandwidth product. So the path compression ratio is very high. So that means that for example, for radar applications, that we can get the highly compressed path. So then we can increase the detection resolution, the range resolution. So there's one example. Another way to generate a microwave is called Optoelectronic oscillator. So it's very similar to an electronic oscillator. You look at the left figure. So this, in fact, is electronic oscillator, consists of an electronic tube. So of course, you can replace it by a transistor to provide the gain. So we need the gain, we need the feedback, positive feedback, and also we need a frequency selection circuit. So here is the LC circuit. So then that the signal, we tape some of the signal through this transformer and send back to the gate of this electronic tube. And if the gain is high enough, then this oscillator will start to generate a microwave. But usually, so LC circuit, you see that the frequency is very low and the phase noise is very high. The stability is not very good. Of course, we can replace this LC circuit by crystal, for example, or pose. So the frequency stability will be better, but still the frequency is low. It cannot be very high. So one solution is using this so-called optoelectronic oscillator. So it is called optoelectronic because you see we have within this loop, the oscillation loop, we have part of it is in the optical domain. So here you look at the configuration here. We have a phase module. We have this MZM, it's a magnetic modulator. So that means that assuming that we have a signal, because the signal usually start to oscillate, so we have noise, and the noise applied to the modulator. Then it's converted to the optical domain and go through optical fiber, and the fiber loss is very small. And apply the photo detector, we get to the signal to the microwave domain, and after amplification, and here we have a filter to select the frequency, we send back. If the gain is high enough, we can use the electronic amplifier, or we can use the optical amplifier before this photo detector. So then that if the gain is high enough, higher than the loss, then it can, so this system can start to oscillate. So oscillator, so it's called an optoelectronic oscillator. The reason we implemented in the optical domain here using long fiber is that because the Q factor, the long fiber, you will have a high Q factor. And the Q factor is high, the phase noise is very low. So that is the key advantage of using this oscillator. We say OEO. Because we can use a long fiber, because fiber loss is small, so the Q factor is very high. So it's higher than, for example, we use a pose, for example. So then the quality is good. Okay, so that is the motivation of using this optoelectronic oscillator to generate a microwave. But the challenge is that because we try to get a high Q factor, the fiber length can be long. But if the fiber length is very long, we know that you see we have the FSR, free spectrum range. Free spectrum range is very small. So that means that you have, you see all the modes very close. You see that the modes close to each other. So it's very difficult to choose to select a single mode because we try to generate a single frequency. So that is very challenging. So solutions, either you use a shorter loop, but Q factor is not very large, so the phase noise is not good. Or you can use dual or multiple loops. You have a few loops, like a fiber ring laser, same thing. We can use 2 loops to make an FSR, effective FSR, bigger. And it's easier for us to choose to select a single frequency. So single mode laser, for example. Same thing here for this OEO. And another approach is called period time symmetry. This is a very new concept that has recently been applied to microphotonics. And we see that if we use this concept, then that here we can, you see the manual to simul ratio can be very significantly improved if you look at this curve. So mathematically, we can prove it, and experimentally also, it is verified. So how to implement, you see, optoelectronic oscillator based on this parity time symmetry. So we can, of course, theoretically, we can, by solving, you see, couple modes equation, we can get a solution, and you can see that one mode is survive, and other modes will be significantly suppressed. But to implement it, usually we need to have two loops. So one, you see here, this the red color represents a loop with gain, and we have another loop, it's a loss. The two loops has exactly the same geometry, same diameter, for example. And also one is gain, another one is loss. The gain coefficient and the loss coefficient must be identical. Then that we say that we achieve this parity time symmetry. Then you will see that one mode will be selected, or the other mode will be suppressed. And I said that this can proved mathematically. So this is, you see the system we demonstrated. We have two loops, one and second loop, and then we can control, you see that by control the PIC, polarizing controller, to change the polarization directions, they can control one loop is higher, the signal can go, you see that easily go through, another one is less easy. So that means that we can get one is gain, another one is loss. So then we get the parity time symmetry. And here is the experimental results. And you can see the phase noise, the one here, the very low one is the phase noise of this oscillator. It's minus 140 dBc per hertz at 10 kilohertz. It's very low. It's much lower than most of this equipment we have in the lab. For example, we have the equipment from Agilent or Keysight now. And that is another example. And as I said that to implement this parity time symmetry, we need two loops and exactly the same geometry. And one is left with the gain, another one with the loss. So it's quite difficult to control, to ensure that the two loops are exactly identical. So one solution is that because of optics, we have a flexibility to do that using a single physical loop, but we try to use two wavelengths. So if we look at this configuration here, we have two wavelengths, and here's the loop. You see here, the loop, they share the same loop. But one wavelength, we try to control the polarizing controller to make one wavelength easily go through this the Magaziner modulator. For example, if this the polarizing direction is in line with the principal axis of this MZM, the light can easily go through. And another one, if it's not, you see, in the same direction, then this the light can be suppressed, largely suppressed. So there's the way to control, you see, the gain or loss. But the two wavelengths are traveling within the same loop, Of course, that if the loop, of course, we'll try to control that loop to make the chromatic dispersion small. Otherwise, you see they are traveling at a different speed. So we may need chromatic dispersion compensation to ensure that the two wavelengths are traveling with the same speed. Okay, then that we achieve this parity time symmetry. Okay, so that is the one based on, you see, use a long fiber to achieve very high Q factor. But this is very effective. And if we do not want to small size, this is the very good way to generate a very high quality microwave, which can find a very important application, especially for example, satellite communications, radar systems. But if for some cases that we need the device very small size, so then of course you cannot use a long fiber, for example, fiber with 1 kilometer long or even 10 kilometers long, which make the entire system very large. So one solution is that to use this so-called whispering gathering mode resonator, the one here. So this resonator, of course, the Q factor can made very large, 10 to the power of 8, for example. Then the entire device can be smaller. So for example here, this is in fact it's a few products from this OE Waves. So this is a small startup in California. and the size can be small. But if you look at in detail, this is not integrated, but still you have PCBs. So that means that the size seems small, but we can make it even smaller. And also, you see the fabrication is very challenging. You see, they have a small PCBs, so it's difficult to have a mass production. So that's why the device itself is very expensive. So then, of course, we have to use PIC, the photonic integrated circuits. So the one example we did a few years ago, based on silicon photonics. So in fact, is that we have, you see here, we try to implement a phase modulator on silicon, and we also implement an optical filter in silicon, and also a photodetector in silicon. But we know that silicon cannot generate light. So at this moment, you see light is coming from external. So we have LED, external LED. So in the future, we try to have, you see that using this heterogeneous integration to integrate this laser diode also on the same chip. But here we have phase modulator, disk, and phase and photodetector on the same chip. So principle is quite simple. So I will explain later on. So how this can be, you see that to implement, you see OEO. In fact, you see that this phase modulation and this optical filter and the photodetector. So the three devices work together is equivalent to a micro filter. And if the output from a photodetector feedback to the input, you see here, feedback the input, we close the loop, then this become a oscillator, but this is integrated oscillator. So here is the experimental results, and the phase noise 10 kilohertz is minus 80. If you compare the one based on the fiber, is minus 140. So this the phase noise is not very good. The reason is that at this moment you see that the Q factor of the second photonic device is a disk resonator is still, the Q factor is not very large. So we have to try to increase the Q factor. For example, we may use the silicon nitride instead of silicon insulator. So the Q factor can be greater. So that is a micro generation. So, and signal processing. Signal processing is that we know that we learn signal processing, and just very important. You see that device in signal processing is a filter. So here we try to discuss how to use photonics to implement micro filter. So here, so just you see earlier we discussed the OEO based on silicon photonics. So here you see I try to show use of phase modulator and phase shift FBG and a photodetector. So the three devices working together is equivalent to a micro filter. So we see how it works. So here you see that you look at this, you see this diagram here, and phase modulator. At the output of phase modulator, we have a carrier, optic carrier, and two sidebands. Compared with a Mach Zehnder modulator, the difference between a phase modulator and a Mach Zehnder modulator is that Mach Zehnder modulator, you have carrier, you have two sidebands, but two sidebands are in phase. But for phase modulator, the difference is that the two sidebands is auto phase. So that is the difference. And then that if we beat, you see that the carrier with one sideband at the photodetector, you get one microwave. Look at the here, you get a microwave. And you beat the carrier with another sideband, you get another microwave. But we said that these two sidebands are auto phase. So then the microwave generated is auto phase. They cancel completely. So that means that phase modulated signal you apply to photodetector, you get nothing. You just a DC. You do not get a microwave. So we know that. The reason is that they cancel. You see that two microwave canceled. But now, if we use our phase shift FBG, we have a deep notch here, and this notch remove this you see here, this sideband. So then that what we have is that we have one carrier and one sideband. Only this sideband survive. So the bit, you see that you can generate, you see microwave. And if we continue to increase the frequency, then that this sideband and this sideband, you see, they cancel each other again. So then the filter you see here, you do not have anything here. So that means that this micro filter, you see, this passband is in fact is copied from this notch, from this optical filter. So that means that we try to have a very narrow band optical filter, and then that this notch is translated to a passband of a microfilter. So this is the principle using a phase modulator, using an optical filter and a photodetector to implement a microfilter. So here, the experimental result, for example, we can tune the wavelength, means that you tune this carrier frequency away from this notch. That means that you see this passband frequency is higher. Closer to the notch, the frequency here, the passband frequency is smaller. So we can tune very easily by tuning the wavelength. Okay, so this is implemented based on fiber optics. So this experiment we did a few years ago. And here you see that this frequency response, the bandwidth is quite narrow. It's only 20, around the 3 dB bandwidth is 20 megahertz. And this frequency can be tunable from a few gigahertz to tens of gigahertz, which is very good. But electronics, usually it's difficult to have an electronic filter with such a big tunable range. Okay, so that is this filter. But as I said, that is based on fiber optics. Fiber optics is not integrated. So people try to translate this same concept to implement it using PIC. So this is one example based on this indium phosphide. Indium phosphide is everything is implemented on a single chip, including a thermal source, a modulator, an optical filter, and a photodetector. So this, in fact, is the first demonstration of using, you see, PIC to implement a microwave filter, tunable microfilter using, you see, indium phosphide. Okay, so the principle is similar. It's not exactly the same, but it's very similar. And so here is the device. It's a packaged device. And so then that this is for this particular example. So it is a low-pass filter. It's a low-pass filter, and I said it can be tunable. It can tunable. But the reason, the key difficulty using indium phosphide is that indium phosphide is the loss is large, so larger than silicon. So the Q factor is much smaller than silicon. So the bandwidth is very wide. So this is simply for demonstration. I believe that it's far from practical applications. But this is the first demonstration using a PIC to implement a tunable microfilter. And of course, we have to here you see here the filter is the optical filter here using indium phosphide. The Q factor is very, very small. So I believe that in the future, so this filter must be replaced by using, for example, silicon nitride to get a narrowband optical filter. Then the entire microfilter should have a narrow passband. Okay. So, but this is really it's integration. It's a PIC for entire system, including data source. Then we also did an experiment where we use silicon. Silicon, you see here, we use phase modulator. We have this optical filter. In fact, it's a disk. This disk is, I think the Q factor compared to a ring resonator, the disk resonator is better. And the photodetector here. So all the three devices are implemented on a silicon chip. But as I said, that silicon does not produce light. So we use an external light source here. And this is the filter. And you see here that this is you see the phase modulated signal. We have a carrier, two sidebands. But because we use a disk to filter out one sideband, so this sideband compared to this sideband here is the height is 12.7 dB lower. So this because of this because of this disk here to remove, you see that one sideband. And then that we get the frequency response here. And this frequency response can be tunable, So here, this experiment, the oscilloscope shows that the spectrum response, which is tuned. And here, if you look at this spectrum response, so the 3 dB bandwidth is around 1.2 gigahertz. Compared to the fiber optics, it's only 20 megahertz. It's still wide, but this is much better than the one based on indium phosphide. Indium phosphide, the Q factor is small, so the bandwidth is huge. So it's cannot be usable. At least at this moment, cannot be used for practical applications. Okay, so that is the second topic. So signal processing. Here, I simply discuss a filter, how to implement a filter using PIC. And then the third topic is two-time delay beamforming. Two-time delay beamforming is, in fact, is used for phase array antenna. So the beam steering. And phase array antenna, the principle is quite straightforward. If you look at this, the one here, the upper figure, you see that we have phase shifters, delta phi, second delta phi, 3 delta phi, and 4 delta phi. So for example, if delta phi equal to 0, so all the phase shift are 0. So if the radio frequency radiates through this antenna array element to the space, if delta phi equal to 0, so then that the beam will be pointing to the horizontal direction because so they have identical phase, along this, you see that horizontal direction in the far field. But if this delta phi is not 0, then that the beam, you see that will be steered. Okay, so but the problem with these phase shifters, this traditional phased array antenna, why it's called phased array? The reason is that we use phase shifters. But the problem with this approach is that if you look at the expression here, the theta is the beam pointing direction, the steering direction, and this theta is a function of lambda. Lambda means it's the wavelength of this radio frequency. So that means that for different frequency, the beam pointing direction is different. Because for example, for signal, for radar, for example, you have a bandwidth. So that means that you have different frequencies within the bandwidth. So different frequencies will be pointing to different directions. So this is the problem called squint problem here, beam squint. So that's why phase array antenna for wideband applications, we cannot use these phase shifters because the beam is, you see here, is squinted. So here is the example here. But now, if we simply replace the phase shifters by time delay line. So tau, 2 times tau, 3 times tau, 4 times tau. And you will see that here, for example, for different, you see that different frequency, all the frequency components will be pointing same directions. So compare the one here with the upper figure, you can see that the beam is not corrupted. So the beam is always pointing the same direction. And if you look at the expression here, theta, it's not a function of lambda here. Here is a lambda, but here is not. So that means that for all the frequency components, for example, you have it's a broadband signal radiated to space. So for example, at the beginning, we said that chirped microwave, the bandwidth is wide, a few gigahertz, for example. Then that we do not have such problem. So all the spectrum components will be always pointing the same direction. So that is the motivation of using this two-time delay. Okay, many different applications. For example, for wireless communications, we have beam forming functions. Then we can point the beam to each user. So to increase the signal-to-noise ratio. So the radiated power may not be very large, but the signal-to-noise ratio can be high. Then how to implement using photonics? So here we use a simple example where we use fiber bar gratings. For example here, so a radio frequency. This is the frequency to be radiated to the space, and I'll try to change the direction, so steer the direction. So modulator, so all the radio frequency is changed to the optical domain at this modulator here to the magnetic source. We can tune the wavelengths. And then they send the signal through, you see that the splitter to this delay line. The delay line consists of these each delay line consists of five bar gratings with different wavelengths. For example, if the tunable source is tuned at lambda 3, then that you see the light will be reflected along this vertical line, and then the beam, of course, we know that will be pointing to the horizontal directions. So the beam pointing direction is perpendicular to this plane here. Now, if we tune the wavelength at lambda 1, so we tune the tunable source lambda 1, so the light will be reflected along this plane here, and then the beam pointing direction, of course, will be pointing downside. You see that because this beam might perpendicular to this plane here. Same thing for this lambda 5. Okay, so simply tune you see the wavelengths, you get the beam pointing direction tuned. But we said that this fiber-based stability is not very good, especially for real phasor antennas. So we not only have 4 channels, we may have hundreds of channels, or even a thousand elements. And then it's very difficult using fiber optics. And people try to use, for example, this is again, you see the earlier I said that we have this laser. You see, use crystal. You see so it's the laser source from the same company. See it's Thales, the French company, and also they did this. Use this. You see that free space optics to implement the two-time delays, and so I will not give the details about this one, but the stability is very good. The size is huge, and they can get you see the beam pointing to different angles, but for different frequencies. So you don't have the beam squint problem. So there is the key. No beam squint using true time delay. But size is huge. So here I just want to show that this one, size is huge. It's very heavy. And then that people try to do it using PIC. So for example here, one example is that we may use silicon resonator. So here, this is a ring resonator. The resonator, we know that you see, for each resonator, you have this group delay response. Here is group delay. So then at different, you see that you can tune this, of course. Tune this ring resonator, thermally tune it, you may get different time delays, of course. And but the problem is that with a single ring resonator is that if you want to get a very high group delay, the Q factor must be very large. Q factor is large means the bandwidth is small. Bandwidth is small, but for this two-time delay, for beamforming, we hope that we have a broad bandwidth. So the solution is that we try to cascade, for example, a few ring resonators. So they in 1, 2, 3, and they have a slightly different central wavelengths. So then that the entire group delay response, you see that is wider. So there is it's wider. So there is the solution to use ring resonator. Ring resonator based on silicon is also very good because size is very small. We can do very small. We have put so many ring resonators on a single chip. So here is it's a 1/8 optical beamforming network, and then we get different time delays, of course. That by tune this thermally tune this, you see the ring resonator, you get different time delays. So here is the measurement of different time delays. You see here different time delays. So this one example, and same group did it more advanced version, and they use more resonators, and the entire device itself. You see, if you compare, you see here, this is euro 20 cents. So the size is quite small, but this you can implement a much smaller size compared to the one here. You see that one here is huge. It's very heavy, and then using silicon photonics, we can do it much smaller. And here's experimental measurement. So the key is that we don't have beam squint problems. Two-time delay, no beam squint. So if you change, you see that the different frequencies. For example, here is it's 1,000 megahertz and 1 gigahertz, 1.15 gigahertz, and 1.3 gigahertz 1.5 gigahertz. So that means the different frequencies, but always pointing the same direction, So that is the key advantage of using this true time delay. So true time delay, beamforming, silicon photonics, and especially in silicon nitride, you see the loss is very small. So can be used to get a large scale integration. And the last topic is a general purpose signal processor. So we try to show that how silicon photonics is used to form a signal processor that is programmable. Look at this, you see here, this diagram here. So for a microphotonic system, usually we have an optical source. Very beginning, in the introduction, I said that a microphotonic system, we have a source, we have a modulator, and we have a processing unit, and then we have photo detector. So then if we have RF in, and here we have RF out. And the processing is done in this optical domain. So for this particular, this example here, this, you see that the processing unit can be reconfigurable. So you can get different, you see that functions. So the key device here is that you look at this, you see here, you have this, you see cells connected. And here, in fact, you have this, this coupler, and you have the heater. You can, by changing this temperature, to make this coupler, it's a Alexander coupler, to be, you see, like a coupler, it's a splitter here, it's a splitter in fact. Or it can be configured as a bar, you see, light will go this way, or like a cross. So this provides flexibility to have, you see, the entire network. You can configure network with different architectures. So, and you can, of course, that if the network is huge, the people try to use neural network to optimize, to get the frequency response you want. But here, show some simple examples. So this effect is a fabricated device. It's very nice. It looks very beautiful. So the device here, and mounted on a PCB. And this in fact is a processor. As I said that this is a silicon photonic, silicon-based. So the source, light source, was not implemented on the silicon. So for this particular processor, only those reconfigurable optical core was implemented based on silicon, and the source is not. Modulator for the detector, in fact, we can do it on silicon, or you can do it using indium phosphide. But light source for sure cannot be done based on silicon. So here, for example, we can reconfigure. You see that this processor to let the light go one, you see, path, so lower path, and the upper path go longer distance. In fact, this is correspond to a two-tape filter. So two-tape is a finite impulse response filter, FIR filter. This two-tape, and here is another two-tape, but here this arm is even longer. It goes through 1, 2, 3 cells. Then this is still a filter, and here this is correspond to a three-tape filter. 1, 2, 3, three-tape filter. So that means that this can be reconfigurable. Okay, so this is a silicon photonic, of course, that we can make it reconfigurable, but the loss, SOI, so silicon insulator, the loss is still very large. So although that theoretically we can, for example, have many cells to make this network very complicated, and then we can try to optimize it to get the frequency response you want. So that means that different frequency response, you can reconfigure it very easily by using a computer, for example. But for a real system, for example, if you have a fabricated device, you will find that the loss is huge. So light coming after certain cells, then all light will disappear. So you do not have a light. So there's the limitation using silicon on insulator. Silicon nitride to make better, you can have more cells. but loss is still a very important issue. So I have to reduce the loss to make the system with a large scale, many cells. So the last example is the one we demonstrated very recently, we published recently. And it's a photonic integrated field programmable disk array signal processor. In fact, you see we have all this disk. So my disk resonator connected, and each of these disk resonator can be tuned, thermally tuned. So that means that, for example, have a light coming, and the light can go different paths. You can control different paths with different time delays. For example, then this can be used, for example, to get, as I said, that beamforming. It's a true time delay beamforming because ring resonator is ring resonator. This is a disk resonator can be considered as a delay line. And you can tune the different time delays. So you get the different time delays. So to get for beamforming, and also you can use it for signal processing. So we said this is a field programmable disk array signal processor. So one example is that we can use it for beamforming. Again, the limitation is that loss. We have a 1, 2, 3, 4. If we have more, you see that more disk is cascaded, then that loss is an issue. So you don't have a good signal output. So that problem must be solved before I believe that this signal processor can be used for real applications. Okay, so that is the last example. It's a general purpose signal processor. Okay, here are my conclusion. So microphotonics has important applications, and especially, for example, for wireless communications, for radar, for signal generation, for example, it's and has been used in many occasions, and also microphotonics can also have is to drive the development of other fields such as sensing. So I think that I have a paper review article in GLT to be published, I think, in the next few weeks, and I don't know if it's already available in you see that the database. It's called microphotonic sensor. We can use a microphotonic to do the sensing. The reason is that a sensor, for example, usually we use a optical spectral analyzer to measure the wavelength change. So that means the speed is very limited, and also the resolution is not very good, and also very expensive. You see the OSA to do the measurement, but we can do it. We try to change the wavelength change to micro frequency change. So micro frequency change, because 1 hertz, even 1 hertz change, we can measure it. So that means that if we change the wavelength change to micro frequency change, we can have much higher resolution. So that is called microphotonic sensor. So that's a paper that is already available. So if you're interested, you can have a look. Okay, the key challenge is that you see microphotonics in the past is very expensive. For the detector, for example, a few $1,000s. And fiber optics, based on fiber, stability is poor. So of course, integration is very important. Silicon photonics, of course, can do most of the work, but silicon cannot generate light. So then we have to go through this heterogeneous integration. That means that with different material systems, indium phosphide, silicon nitride, for example, the loss is low, or silicon insulator. And we can also CMOS, for example, CMOS, we can have digital electronics. If we put everything on a chip, so then we really have a system on chip. And for many important applications, including these wireless communications, sensors, or radar, whatever. Thank you very much. I think I stop here. Thank you.
Thank you very much, Professor Yao. I have a round of virtual applause. Thank you. Questions, I suggest that you can either enable your microphone, unmute yourself and directly ask questions, or you could type it in the chat and I can read it out.
Yes, I can see.
Oh, so there's a question from Victor Chan. It says, thank you, Professor Yao, for the great, interesting talk. As a communication engineer, I'm really fascinated by the broad application of microwave photonics. If these new devices are to be implemented in wireless communication systems, can the existing design, like signal modulations, signal detecting schemes, still be used? Or do we need to design new algorithms to make that work?
Okay, so that's a very good question. You see that for wireless communications, so one very important application of this microwave photonics to this wireless communication is that it's called radio over fiber. So because you see that the signal itself, for 5G or current generation 4G, it's a wireless. It's a radio signal, so radiated to space. But if we want to distribute this radio signal, for example, for in the subway, for example, we don't have signal. So one possible way people also did that is that we use fiber to send this wireless signal to different locations with antenna radiated to the space. So then that the entire subway or shopping mall can be covered by all these small cells connected by optic fiber. So that means that the radio signal is modulated on optical carrier and sent through fiber and sent to the you see different antenna and radiated to space. Then you can cover all the corners, so with a very low cost. So that is a very important application of microphotonics. It's called radio over fiber. That is for radio signal distribution. And I believe in the future, for example, for 5G, and 5G now currently 5G, the frequency is not very high. It's less than 6 gigahertz. So the distance can be long, but in the future, people try to, because the data rate is higher and then the carrier frequency should be higher. So the internet loss is an issue. So because you see the millimeter wave in free space, the loss is very high. So the way is that we may use fiber to distribute the signal to along the, for example, highway. So then that you still can get access. Okay.
Okay, thank you. So I guess the distribution is highly enabled, but the algorithm and the design is not, doesn't really need to be changed.
No. You see, because you see that for photonics, you see, for the wireless communications, mainly for the distribution. But for this wireless communication, the signal still is wireless. It's a radio frequency.
Right.
It's not the optical frequency.
Yeah.
Yes.
Okay, sounds good. Any other questions? There's some more. Okay, here's Elias Softman, and thank you, Professor Yao, for the lecture. On slide 48, do the heater bars physically contact each other to accomplish coupler bar cross functions?
Okay, yes, 48, I think it's, you mean this one?
It's the honeycomb, yes.
So I think it's the heater, it's better that to be, you see the heater is, it's isolated. You do not want to have mutual coupling. So that is better. But in real situation that the heater may have, you see, you have one heater, when it's heated, may have coupling to another one. But for good use is that it's better that it's isolated.
Okay, great, thank you. Next question, a very basic question. It says, a very basic question, why a long fiber can bring high quality factor?
Okay, so I think that simple understanding is that, for example, the Q factor, we calculate Q factor is Q, usually we use the equation is It's the center frequency, F0 divided by delta F. Delta F means that the bandwidth. For example, if the center frequency is 10 gigahertz, and the bandwidth is 10 megahertz. So 10 gigahertz, 10 megahertz, you get the Q factor is 1,000. Okay, now why longer fiber? So longer fiber means that FSR, you can see that FSR is smaller. The bandwidth becomes smaller. So this is a simple way to understand. But the real understanding is that you see, it's the longer fiber, you can store the energy. So this is Q factor. In fact, is the cavity, how the capability of the cavity to store energy. For example, if the loss is 0, for example, we have a vapor parallel cavity. If the loss is 0, so the light will resonate always, you see, for a long time in the cavity. So that means that the bandwidth is 0. If really the loss is no loss is 0, you see the resonance in the cavity for forever. So the bandwidth, if you calculate bandwidth is 0, so the Q factor is infinity. So longer fiber means that the ability to store the energy is higher. Well, a simple way to understand, as I said, that is F0 divided by delta F. Delta F, of course, FSR, free spectrum range is smaller. Longer the distance, free spectrum range is smaller. Free spectrum range is smaller, bandwidth is smaller. So for fixed center frequency, if delta F is smaller, the Q factor is larger.
Very good, very intuitive explanation. Okay, next question from Neil Choksey. Apart from the fabrication challenges, what are some of the other challenges in realizing microwave photonics using resonators and using PIC? So
okay,
it's asking about challenges.
Okay, so
I guess.
Yes, go ahead.
Yeah, I guess one of the things you mentioned is loss as being one of the challenges, I guess. I guess the question is, what are some of the major challenges in particular related?
Yes, one challenge is that you see for microphotonic systems, it's we need you see we need source. So that means that silicon itself cannot produce light source. So that we have to use different material systems. So that is fabrication, of course, is the fabrication challenge. And another one is that material loss. You see the loss is large. So for some applications that the loss is too large to make the system is hard to be used. And especially that for the microphotonics functions, it's analog processing. In fact, it's analog processing. So it's not a digital. Digital usually you have noise, but it's not. At least you can completely eliminate the noise. Digital, but the analog is very difficult. So the only way is a filter. It's filter. So loss, I think, is it's a very big challenge.
Okay,
yeah.
Thank you very much. Yeah, I think we've actually passed our time, so thank you so much. There's lots of questions, but I think we should end the talk now. Thank to Professor Yao again, and thank you for all of you for participation, and I hope to see you next time. All right, so everybody can just sign off.